What if I told you the next app you download wasn't built by, a tech company in Silicon Valley, but by a virtual CEO, a virtual chief technology officer, and like a whole team of AI coders that only exist inside a server rack?
And they built the entire thing in about 3 minutes.
Right, exactly. Welcome to the deep dive. We are unpacking a massive paradigm shift today. The fundamental blueprint of software creation is, well, it's being entirely rewritten right now.
It really is. It's a profound transition we're looking at.
Yeah, and our roadmap for this is a recent state-of-the-art concept paper. It's by researchers Young-Jian Tang and Thomas Runkler, called LLM-based agentic systems for software engineering.
Right, and the core focus there is...
Oh, yeah. The mission today is to look at how we are moving away from single AI chatbots, the ones that just answer your questions, into this whole new era of multi-agent systems.
Exactly. We're talking about digital squads.
Right, squads that debate, collaborate, and execute these complex software projects from the ground up.
Yeah, we are moving out of the phase where artificial intelligence functions as, a glorified search engine or just an autocomplete tool.
Right, just hitting tab to finish a line of code.
Right, right. We're moving into an era of autonomous orchestration. It is no longer about generating a localized block of text or, say, a quick Python script.
It's way bigger than that.
Much bigger. It is about architecting, building, and refining entire functioning software ecosystems without human hand-holding.
Okay, let's unpack this. Because I think when most people, when you or I hear AI coding, we picture opening a browser window, pasting a prompt into a single chatbot, and just waiting for it to spit out a chunk of code.
Which is how it worked for a while, yeah.
But Tang and Runkler are arguing that for real, enterprise-grade software engineering, a single large language model just hits a brick wall. So why is one massive brain not enough anymore?
Well, to understand the bottleneck, we really have to look at the underlying mechanics of how these models evolved.
Okay, take us back.
So go back to the early days of transformer architectures, right? Models like BERT.
Right. BERT.
The breakthrough there was their highly parallelizable architecture.
Wait, parallelizable, meaning it processes all the words in a document at the exact same time instead of reading left to right sequentially like a human does.
Precisely. And because it processes everything at once, it can capture long-range dependencies.
Which is a big deal in software.
It's critical. I mean, a variable defined on line 10 might not actually be used until line 10,000.
And transformers allowed the system to actually hold that connection.
Yes. So as researchers scaled these models up, feeding them more data and compute, they developed what we call emergent abilities.
Like step-by-step reasoning.
Right, or in-context learning. But here is the friction point. Complex software development is not a single isolated task.
It's a massive tangled web.
Exactly. You have requirements gathering, system architecture planning, coding, security auditing, and continuous stress testing.
And if you ask one AI model to do all of that simultaneously, what happens? Does it just, crash?
It suffers from context degradation.
Context degradation. Okay, what does that mean in practice?
Well, every large language model has a context window, which is basically a strict limit on how much information it can hold in its active memory at one time.
So it just runs out of space.
Yeah, if you force a single model to act as the project manager, the coder, and the security auditor, its context window just gets completely flooded with conflicting instructions.
So it loses the thread.
It loses the thread of the original architecture.
Yeah.
It forgets a security rule it defined 5 minutes ago because it is, too busy trying to fix a syntax error.
Wow. Okay, so the solution to overcoming that context limit is a multi-agent system.
Exactly.
So it's like, instead of a one-man band desperately trying to play a kazoo, a drum, and a guitar all at the same time while reading 3 different pieces of sheet music.
Which never sounds good.
Right, exactly. Instead of that, you build a symphony orchestra. Everyone is a master of their specific instrument.
Yeah. That is a highly accurate way to visualize it, yeah.
But it's not just that they play different instruments, right? It's how they pass the melody back and forth without losing the tempo.
Yes, and by dividing the labor like that, you achieve 3 structural advantages.
Okay, what's the first one?
First is specialization. You can give one agent a system prompt that says, your only goal in life is to write hyper-efficient database queries.
Okay.
And then you give another agent a prompt that says, your only goal is to aggressively break those database queries.
Oh, I love that. So they are optimized for opposing highly specific goals.
Right.
Which creates like a productive tension. The system gets stronger because its internal parts are basically fighting each other in a controlled way.
Precisely. Now, the second advantage is modularity.
Modularity, like Lego bricks.
Kind of, yeah. Think of it like swapping out components in a stereo system.
Okay, yeah.
If a revolutionary new vulnerability testing technique drops tomorrow, you don't have to retrain your entire massive AI infrastructure from scratch.
Oh, that saves so much time.
Huge amounts of time. You simply upgrade the tester agent with the new methodology, and the rest of the multi-agent system just keeps humming along.
Wow. And the third advantage.
Finally, you get parallelism.
Right, doing things in the same time.
Yes. The planner agent can be designing the next feature while the tester agent is still validating the previous one. It compresses the development timeline exponentially.
Man, having a digital orchestra sounds incredible in theory, but I really want to see the assembly line in action.
It's fascinating to watch.
Like, how does this AI symphony actually compose a piece of software from scratch? Because, software doesn't start with code. It starts with somebody wanting a product to do a specific thing.
Right, the human desire part of it.
Yeah, so let's talk about requirements engineering.
Well, requirements gathering is arguably the most critical and honestly nuanced phase.
Because if you build the wrong thing perfectly, it is still the wrong thing.
Exactly. You have to translate vague human desires into strict logical system parameters.
Which humans are bad at doing themselves anyway.
True. But the research points to a specialized multi-agent framework called MARE, which is dedicated entirely to this phase.
MARE, okay.
And MARE doesn't just ingest a prompt and spit out a summary. It systematically executes 9 distinct analytical actions.
Wait, 9 actions? What does that actually look like under the hood?
Well, first, it systematically extracts entities like user, database, or payment gateway from the raw text.
Okay, so identifying the pieces.
Right. Then it maps the relational dependencies between them.
How they connect.
Exactly. And then it actively searches for edge cases. It's asking itself, what happens if the user disconnects during a payment?
Oh, wow. It's anticipating problems before the code even exists.
Yes. It builds comprehensive state diagrams before a single line of code is written.
That's incredibly thorough.
And by breaking the planning phase into these distinct actions, MARE actually beats baseline single-prompt AI models by over 15% in accuracy.
That is a massive jump. Okay, so MARE builds the blueprints, but how do we know the blueprints are actually structurally sound?
Because a blueprint might look great on paper, but collapse in the real world.
Exactly.
That is where another framework called SPEGEN enters the pipeline.
SPEGEN, what does that do?
SPEGEN takes the rules generated by the planning agents and applies what are called mutation operators.
Mutation operators. That sounds like something from a genetic engineering lab.
It really does, and the concept is actually very similar.
How so?
Well, a mutation operator deliberately injects a logical flaw or a contradiction into the software specifications to see if the system's own verification tools catch it.
Wait, it essentially sabotages its own blueprints.
Yes. If the system fails to notice the mutation, the AI knows its rules aren't robust enough and it rewrites them.
It is stress testing its own logic. That is wild.
It's highly effective.
So once we have a fully mutated, stress-tested blueprint, we move to code generation.
Right, the actual building phase.
Here's where it gets really interesting. Tang and Runkler detail a framework called pair coder.
Pair coder, yes.
And this is where it gets highly collaborative, right? Pair coder uses a navigator agent and a driver agent.
Just like human pair programming.
Yeah, exactly. The navigator acts as the senior architect, proposing high-level solution plans and directing the flow.
While the driver is the one actually on the keyboard.
Generating the syntax, compiling it, and refining it based on the navigator's feedback.
It's a very elegant system.
But I have to ask, isn't having 2 separate AIs doing the job of one just burning unnecessary compute? I mean, why not just have one model plan and type?
It all comes back to separating logic from execution.
Okay, unpack that for me.
Well, generating syntactically perfect code requires intense focus on the micro level, right? Semicolons, variable scopes, memory allocation.
The tedious stuff.
Right.
Yeah.
But planning requires macro level focus.
The big picture.
Yes. And if you force an AI to do both, it often prioritizes getting the syntax right at the expense of the overall architectural elegance.
Ah, so it loses the forest for the trees.
Exactly. Pair coder isolates those cognitive loads. The navigator only evaluates logic. The driver only worries about execution.
That makes a lot of sense. You don't want the person steering the ship to also be shoveling coal into the engine.
It mimics human pair programming perfectly.
So the code is written. But even with a great driver and navigator, code is practically useless if it hasn't been audited for security.
Right, which brings us to static checking.
Reviewing code without actually executing it.
Exactly.
The paper introduces a framework called GPT-LNS. And the way they set this up is essentially a digital courtroom, right?
The courtroom dynamic is totally central to how GPT-LNS functions. You have a pool of auditor agents.
Okay, the auditors.
Their sole directive is to hunt through the codebase for potential vulnerabilities.
Like buffer overflows, injection flaws, that kind of thing.
Yes. And when they find something, they don't just flag it. They have to articulate a logical argument for why it is a vulnerability.
They have to present their case to the judge.
Exactly. And the judges are the critic agents.
The critics, okay.
The critics take the auditor's arguments and score them against strict security criteria.
So what happens if an auditor flags something silly?
Well, if an auditor flags a variable name it doesn't like, the critic will just dismiss it as a false alarm.
Oh, that's smart.
This dual agent setup drastically reduces the hallucination rate.
Right, where AI confidently claims a bug exists when the code is perfectly fine.
Exactly. It filters out the noise.
Okay, so we have planners, coders, auditors, and critics. But the paper takes this structure even further.
I really do.
They highlight a system called Code Agent, which simulates a literal, full-scale corporate hierarchy.
This is a fascinating model.
We are talking about an AI CEO, an AI Chief Product Officer, an AI Chief Technology Officer, all managing lower-level AI coders and reviewers.
It's literally a virtual tech company inside your computer.
But I have a major piece of pushback here.
Go ahead.
If you have an AI CEO, a CTO, and a senior coder all arguing over how to implement a feature, doesn't that just create digital middle management chaos?
I mean, it certainly could.
Because humans get stuck in endless unproductive meetings all the time. How do a dozen language models not just trap themselves in an infinite loop of, as per my last email?
That is the exact friction point researchers had to solve, and it is why the paper heavily emphasizes agent communication protocols.
Okay, protocol.
You absolutely cannot just have 5 language models generating raw text at each other simultaneously.
Because the system would just collapse into noise?
Exactly. They need rules of engagement.
Right, like an air traffic control system.
Precisely. This is what protocols like the Contract Net Protocol, or CNP, and the Model Context Protocol, MCP, provide.
Tell me about MCP.
MCP is fascinating. It is an open standard that dictates the exact data packet format agents must use to interact.
So no casual chatting.
Right. When the auditor agent finds a bug, it doesn't just yell "broken" into a shared chat window.
Right.
It wraps that bug report in a highly specific JSON format, assigns it a severity score, and routes it directly to the critic agent's specific queue.
Wow, so it forces them to communicate in highly structured machine logic rather than conversational English.
Yes.
Which totally prevents that endless back and forth debate.
Exactly. MCP also standardizes how these agents use external tools.
Like what?
Well, if the AI CTO needs to query a database to check a historical log, MCP ensures it uses the exact same authorization pathway as the AI coder, so they don't lock each other out of the system.
Oh, that's brilliant. It replaces middle management chaos with absolute deterministic routing.
It keeps everything moving smoothly.
Okay, so the communication is locked down. The virtual company has planned the code, written it, and audited it. But what about actual execution testing?
The dreaded testing phase.
Yeah, I know from human developers that writing unit tests to cover every possible user action is often the most tedious, soul-crushing part of the job.
It is notoriously difficult for AI as well, actually.
Really? Why?
Because a test must be syntactically flawless and anticipate states the software hasn't even entered yet.
So how do the multi-agent systems handle it?
The paper highlights a system called cover-up, which solves this through iterative execution tracing.
Iterative execution tracing. Okay, break that down.
Cover-up writes a batch of tests and runs them. Then it physically traces the execution path through the code base to see which specific lines of code were never triggered by the tests.
Oh, so it finds its own blind spots.
Yes. Once it identifies a block of untested code, it dynamically rewrites its own system prompt, instructing itself to specifically target that isolated block.
Wow.
And it just loops this process until the test coverage hits the required threshold.
And when one of those tests inevitably fails?
Yeah.
Because, I mean, no code is perfect on the first try.
Oh, definitely not.
I know human developers who spend 3 days just hunting for a missing semicolon. How does a multi-agent system handle debugging without just blindly changing variables and guessing until the error message goes away?
Well, blind guessing is a massive problem with single-agent systems.
Just throwing spaghetti at the wall.
Exactly. But in multi-agent frameworks, we see the application of scientific debugging.
Scientific debugging.
A standout system here is AutoSD. AutoSD mandates that the AI agent follows the actual scientific method.
Wait, how does an AI run a science experiment on code?
When a test fails, the agent is forced to generate a formal hypothesis about the root cause.
Like what?
For example, I hypothesize the crash is caused by a null value being passed from the payment API.
Okay, a clear hypothesis. Then what?
Then it designs an execution-based validation, an experiment. It injects a tracking variable specifically to watch that payment API value.
To see if its guess was right.
Right. It runs the code. It analyzes the output logs to confirm or deny its hypothesis.
Wow.
And only after the hypothesis is proven does it actually attempt to write a patch.
So it is reasoning through causality, not just throwing syntax at a wall.
Exactly. It's a huge leap forward.
A digital company with an AI CEO, CTO, and a team running rigorous scientific debugging sounds incredibly potent.
It is.
But, to run an infrastructure that smart, you need monumental computational brainpower.
Yes, you do.
Which brings us to the engine room. Where are these frameworks getting their intelligence? And more importantly, is it actually safe for a real-world enterprise to hand over their entire software pipeline to them?
Well, the effectiveness of any agentic system is entirely tethered to its underlying foundation model.
The brains of the operation.
Exactly. And Tang and Runkler outline two distinct pathways here: proprietary models and open source models.
Right. The proprietary models are the big household names.
Yes.
OpenAI's GPT-5, Google's Gemini 3 Pro, Anthropic's Claude v4.5. The paper refers to these as the performance upper bounds.
They are the smartest, most capable brains available.
Right.
They are the upper bound of reasoning capability. But utilizing them introduces a critical vulnerability, which is data privacy.
Because you have to send your data to them.
Exactly. To leverage a proprietary model, an agentic framework must send its requests out over the internet via an API to OpenAI or Google servers.
Which is a huge red flag for a lot of companies.
Oh, absolutely. If you are a major financial institution or a defense contractor, your proprietary source code is your most guarded asset.
Yeah. Sending unreleased, highly sensitive architecture over an external API is a security non-starter.
Completely unacceptable risk.
It's like hiring the most brilliant software consultant on Earth to build your top-secret project. But that consultant insists on working out of a crowded public coffee shop where they might accidentally leave your trade secrets on a table.
That's a perfect analogy.
So the alternative, according to the paper, is relying on open source models.
Right, models like LLM-A4 or DeepSeek V3.
You take the model, you pull it behind your own corporate firewall, and you run it locally.
Yes.
It's like building an in-house team in a secure facility. But wait, let me push back on this.
Okay.
Hosting a massive state-of-the-art model like DeepSeek on your own servers requires insane GPU compute. For a mid-sized company, isn't the millions of dollars in hardware cost just as prohibitive as the privacy risk of an API?
You have correctly identified the core tension of local deployment, yes. However, the researchers highlight a recent paradigm shift that dramatically alters that cost-benefit analysis.
Okay, what is that?
The rise of reasoning-optimized architectures.
Reasoning-optimized architectures, how do those change the math?
The prime example cited is DeepSeek R1. Traditional models scale performance simply by getting larger, requiring more parameters and therefore more GPUs.
Just brute forcing it with more hardware.
Exactly. But reasoning-optimized architectures take a different approach.
How so?
Instead of just predicting the next word based on massive size, they are trained to spend more of their computational budget on internal logic before they output a response.
Oh, they sit and think before they speak.
Exactly. They generate hidden chains of thought, exploring multiple logical pathways, discarding dead ends, and verifying their own math internally.
Wow.
For complex tasks like architectural decision-making or scientific debugging, this is revolutionary.
Because it's doing the hard work up front.
Right. A smaller, reasoning-optimized model running on a localized, affordable server cluster can effectively trace the logic of a massive code base just as well as a colossal proprietary model.
So you basically bypass the hardware bottleneck entirely.
Exactly.
Okay, so let's synthesize this.
Sure.
We have reasoning models that can run securely in-house. We have multi-agent frameworks that act as CEOs, coders, and courtroom judges.
Yep.
We have air traffic control protocols like MCP, keeping everything organized.
All working together.
So what does this all mean? If all of this functional architecture exists right now, why isn't every human software developer out of a job today? What is the reality check?
Well, the reality check is found in Section 5 of Tang and Runkler's paper.
Ah, the roadblocks.
Yes, it outlines the severe bottlenecks preventing full, hands-off automation right now.
Okay, what's the first one?
The first major roadblock is a profound lack of deep niche expertise.
Wait, I thought the whole point of multi-agent systems was specialization.
They are specialized in structure, but generic in knowledge.
Generic in knowledge. What do you mean?
A framework can assign an agent to the role of security auditor, but that agent still relies on the generalized training data of its foundation model.
Ah, I see.
It knows what a typical SQL injection looks like. But if you need an agent to hunt for a zero-day vulnerability...
Well, wait, meaning a totally novel, undiscovered flaw in a specific cryptographic library that no one has ever seen before?
Exactly. Finding a zero-day requires extreme domain-specific intuition and a deep understanding of obscure hardware interactions.
Which AI doesn't have yet.
Right. Current agents are playing the role, but they lack the PhD-level depth required for the hardest 1% of engineering problems.
Okay, that makes sense. And there's also a massive data gap, right?
Sure.
Because an AI learns from what we feed it.
Yes.
And we feed it millions of GitHub repositories. But building software in the real world requires a vast amount of invisible data.
That invisible data is the connective tissue of software engineering. The final code is just the physical output. What the AI does not see are the whiteboard architecture diagrams that were erased 3 months ago.
Oh, man, yeah.
It doesn't see the messy, sprawling developer discussions on Slack.
It doesn't see the frantic message from the lead engineer 3 years ago saying, hey, whatever you do, don't use this specific routing library. It inexplicably crashes every Tuesday.
Exactly. Because agents only ingest the static, finalized text of the code base, they totally lack the historical and human context.
That's a huge blind spot.
It is. Without that invisible data, an AI CTO might confidently redesign a system architecture, completely unaware of the institutional knowledge that makes its new design a terrible idea.
Which brings me to the human element.
Right.
Where do you and I actually fit into this new paradigm? If the AI is gathering requirements with pair programming with itself, and debugging scientifically, are human developers just becoming babysitters?
It's a valid concern.
Like, are we just the ultimate super reviewers blindly clicking approve on pull requests?
Yeah. Well, the integration of humans is categorized in the paper as human-agent coordination. And it is perhaps the most critical unsolved challenge right now.
Unsolved.
Yes. Humans are absolutely necessary to provide that invisible context we just discussed. The problem is identifying the precise intervention points.
Intervention points, like knowing exactly when to step in.
Yes. It is a Goldilocks problem.
How so?
Well, if the multi-agent system pauses its work to ask a human for clarification every 5 minutes, you completely lose the speed and parallelism of automation.
You have just built a very annoying system that constantly interrupts you.
Exactly. But on the other hand, if the system never asks for help, it might confidently spend 6 hours building a massive, intricate architecture that is fundamentally wrong for the business context.
So that's bad. So we need to be the conductor of the orchestra. But right now, the system doesn't know how to gracefully accept direction without stopping the music entirely.
Precisely. Designing a framework where a human can step into the loop, inject a critical piece of historical context, and step seamlessly back out without crashing the multi-agent workflow is a massive area of ongoing research.
And speaking of knowing if the orchestra is even playing the right song, how do we evaluate these systems?
That's another big issue.
If they are this complex, our old grading rubrics must be completely obsolete.
They are fundamentally broken for this paradigm.
Wow, broken.
Yeah. Our current industry benchmarks, like Human Evil or Bug Bench, evaluate a single AI on an isolated static task.
Right, the prompt is essentially, here is a mathematical logic puzzle. Write a standalone Python script to solve it.
Exactly.
Which is easy to grade. It either outputs the right number or it doesn't.
But software engineering is not a series of isolated logic puzzles.
Not at all.
It is inherently collaborative and continuous. It involves joint requirements gathering, real-time integration, and constant peer refinement over months.
None of which is in those tests.
Right. We simply do not have the metrics to properly grade an entire virtual company of AI agents working collaboratively on a legacy codebase.
Oh, I see.
Using human evil to test a multi-agent system is like trying to review a full symphony orchestra by only listening to the first violinist tune their instrument.
You completely miss the interaction entirely.
Exactly.
So to bring this all together for you listening, why does this actually matter to you?
It matters a lot.
Right. Whether you are prepping for a tech sector board meeting, leading a non-technical department, or honestly just wondering why the apps on your phone update so quickly, you need to understand that the fundamental mechanics of the digital world are shifting underneath our feet.
They absolutely are.
We are moving from an era of humans manually typing lines of syntax to an era of humans managing automated specialized digital squads.
Yes.
The speed at which software will be prototyped, tested, and deployed is going to compress in ways that will disrupt every single industry relying on technology.
And I will leave you with a final thought to consider, building on that concept of modularity we discussed earlier.
Right.
The core strength of these frameworks is that individual agents, the tester, the auditor, the driver, they can be dynamically swapped out or upgraded without breaking the overall system.
Right, the interchangeable cogs in the AI factory.
Now, project that trajectory forward. We have orchestrator agents, AI CEOs, and CTOs that are already capable of reasoning, planning, and evaluating the performance of their subordinate agents.
Yeah.
How long until an orchestrator agent analyzes its own team's workflow metrics and realizes that a specific entity, perhaps an outdated AI coder, or perhaps the human reviewer, is the primary bottleneck?
Oh, wow.
How long until that orchestrator decides it is more efficient to simply program, test, and deploy its own specialized, upgraded replacement agent to permanently optimize the team's output?
To essentially fire the weak link.
Exactly. We are building autonomous systems designed to relentlessly solve complex engineering inefficiencies. Eventually, the makeup of the engineering team itself becomes the inefficiency it decides to solve.
It's a digital orchestra that might eventually realize it can play a much faster, more complex symphony if it just gets rid of the human conductor.
Precisely.
Well, next time you open a flawless, deeply complex application on your device, take a second to think about the invisible virtual company that might have built it from scratch while you were sleeping. Thanks for joining us on this deep dive.